Today we're going to do volume by cross-section. This follows our previous section pretty well because in order to find the volume of a solid, what we're going to do is we're going to have to first find the area of a region, the area between a couple of functions oftentimes. And then once we get that area, what we're going to do is multiply that area by a thickness, and that's going to give us a volume. And so we're going to have the volume of all kinds of slices. We're going to add the volume of each of these individual slices together. And we're going to have a more accurate feel for what the actual volume is if we make more and more and more slices. In fact, what we'd like to do is we'd like to make an infinite number of slices. So we are going to multiply the area of the slice by the thickness, and that gives us the volume of each one. And if we add together an infinite number of them, the areas times the thicknesses, we'll get the volume. But our tool for adding an infinite number of things together, areas times thicknesses or volumes, our tool that we'll use is the integral. And all we have to do is tell the integral where are we starting, where are we ending, and you go ahead and add all of these volumes together for us. Now, difficult to picture what these solids look like. In the classroom, we're going to have a model of these things, and we can actually see what they look like. But the fact if you can see it or if you can't see it, it doesn't change the procedure we're going to use for finding these volumes. We're going to have an object with a circular base, and so what I've got here is I've got a top view of this situation. And we're going to take this top view of this circular object, at least from the top it looks like a circle. We're going to put it square on the center of the XY axis, right on the origin. We've got a solid with circular base, and the radius is 4. So I'm going to draw a little radius here. Draw a radius of 4. And then it says, let's slice. Let's find cross sections that are perpendicular to the x-axis. So I'm going to slice this thing perpendicular to the x-axis. And in my drawing, I will always start my slice at the end of that radius. It's going to have a slope. And what I do is I take that slice and I pick it out of there. I stand it up over here. Again, looking down from the top. What I'm going to do now is I'm going to push this slice over. When I push this slice over, what it tells me is that this cross section is a square. When this thing falls over, this very thin slice, then I'm going to get a square. Now, all I need is the area of that square because the integral of area times thickness is going to be the volume. So, in an effort to find area, I'm coming back to my drawing here. And where I slice this will vary. So that distance, x from the origin, is going to vary. And if that's x, well, I guess this distance is y. And since this is a nice symmetric circle, we're going to have a y down there, which means that this slice right here that I stood over here has a side that is 2y. And if I'm interested in the area, well, I take my 2y times 2y, and I'm going to get an area of 4y squared. Now that's great, but that's the wrong variable. As we learned when we were finding the areas of in between curves, if your slice hits the x-axis, you better have everything in terms of x. If I'm going to set up an integral, the integral of area times thickness, everything better be in terms of x, and right now my area is in terms of y. But what I do know from my drawing is that x squared plus y squared is going to be equal to the hypotenuse, or 4 squared. So I'm going to get 16. And so if I'd like an expression for y squared, I could say that it is 16 minus x squared. And that's going to help me come up with an expression for the area in terms of x. I'm going to take 4 times y squared. 4 times 16 minus x squared. I'm going to say that the area is 64 minus 4x squared. And now that I've got the area in terms of the correct variable, my battle is half won. The volume will equal the integral of the area times the thickness, and the thickness of each slice is this very small change in x. But now I need a lower limit and an upper limit. Again, I come back to my drawing. This solid starts way over here. The x values start way over here, and they end here. So if this is a circle with radius 4, I think we're starting at -4 and ending when x is +4. So at this time, I'd like you to press pause. I'd like you to put this into your calculator and see what you come up with. And then start it back up and see if your area agrees, or your volume agrees with mine. Because I got 341.3. And I'm kind of hoping you did too, because that means I didn't mess up. Now, in the second example, we again have this solid with a circular base. I'm not sure three-dimensionally what this looks like, but if I look down from the top, I see a circle and I center it on the origin. Now, this particular circle has a radius of 5. And I'm going to slice cross sections perpendicular to the x-axis. I'm going to take that slice and I'm going to stand it up on edge over here. And then I'm going to push this slice over so I have a better idea of what it looks like. And when I push it over, the shape of the figure that I get is an equilateral triangle. Well, now I've got to find the area of an equilateral triangle. Again, this side's going to be x, this side's going to be y. This length, because of symmetry, is also y. And so this side right here is 2y. Now, how do you find the area of an equilateral triangle? Well, we'd have to revisit geometry. We'd have to realize that every angle of an equilateral triangle is 60. And we'd want to take the base times the height divided by 2. We'd have to realize that we've got a couple of 30, 60, 90 triangles. And we'd have to use the rules of 30, 60, 90 that we learned back in geometry. Or we could just maybe mesmerize the formula for area of an equilateral triangle. That's an equal, I better put an E there. Area of an equilateral triangle is the side squared times the square root of 3, all divided by 4. And that can be proven using the rules of 3069. Well, in our triangle, if I take one of these sides, which are all the same, square it, multiply by the square root of 3, and divide by 4. I've got the area of this slice of my three-dimensional object. And again, that's half the battle. The volume is the integral, or the sum of all of these areas times the thickness. But now I got another issue here. I've got the wrong variable. I've got y's, I need x's. Well, we have the same relationship here. X squared plus y squared, in this case, is equal to 25. And so y squared is 25 minus x squared. So when I make that substitution into my area formula, I'm going to take y squared, which is 25, minus x squared. I've got to remember to multiply by this square root of 3, which I can do inside the integral, or I would tend to treat it like a coefficient and pull it out front. I've got to remember to multiply by the thickness of each slice, and realize that this figure starts over here at what would amount to -5 and end over here at +5. So, time to pause, use your calculator, and then revisit. And when you revisit, I think we're coming up with a volume of 288.675-ish. Third example, we don't have a circular base. The base of this triangle, or the base of this solid, is a triangular region. It uses the y-axis and the x-axis, and the line y equals -2x plus 4. Now, if I were to graph that line, I'd have to have a y-intercept of 4. I'd have to have a slope of -2. And so I think we'd end up with a region that looks like that, using the x-axis, the y-axis, and that line. Again, cross-sections are taken perpendicular to the x-axis. I take that slice, I bring it over here. Again, looking down from the top, don't know what shape it is, but I'm told to push this thing over. And when I do, I get an isosceles triangle. And I better say an isosceles right triangle. An isosceles right triangle with one leg on the base. Well, this thing right here, this is, I'm looking down, that's resting on the XY axis. And when I move it over here, this is what was resting on the base. This is was resting on the XY axis. When I push it over, that is one of the sides of this isosceles right triangle. Now I need to find the area of this triangle. And this distance here, well, that varies, so I'm going to call it a variable, and it is a y value. And it keeps changing as I move along from left to right or right to left. If this is isosceles, this is y. And so the area of this triangle is base times height divided by 2. That's the area of the triangle, and as always, it's in terms of the wrong variable. So, what's an expression that involves both x and y? Well, I'm told that y is equal to this, and that is in terms of x. So I'm going to say area is negative 2x plus 4. That's what's got to be squared and divided by 2. That is the area of every single slice. And if I take the integral of this area, and I'm going to pull that 2 on the bottom out front by calling it a half. This is the area of each slice. I'll multiply by the thickness of each slice, and then come back to the original drawing to see where does this region begin, where does this region end in terms of x. Now it's pause and calculator time. And hopefully we agree that the answer for this one should be 5.3 repeating. Example 4, and we're not going to do example 5, so this is our final example. We've again got the same thing happening. We've still got this triangular region. And you know what? I'm going to try this a little differently. I'm going to go I've got this triangular region, and I am going to slice perpendicular to the x-axis. But this time, when I bring my cross-section over here, and I push this thing over, this time I'm going to get a semicircle. When I push this thing over, I got myself a semicircle. Now this distance from line down to the x-axis is some measurement of y, and it keeps varying. But if I'm looking for the area of this semicircle, I'm going to have to take this distance, which is y, and I need to turn that into a radius, and I believe the radius of my semicircle is going to be y over 2. And the area of any semicircle is pi times the radius squared divided by 2. So I'm going to get pi y over 2 squared divided by 2. And if I were to multiply this out correctly, I believe I'm going to have pi y squared over 4 divided by 2, or y squared over 8. That's the area of this semicircular slice. So the volume is going to be the integral. Again, starting at 0 and again ending at 2. And everything's got to be in terms of x. I might pull the pi over 8 outside the parenthesis, outside the integral, or leave it in. Either way doesn't matter. And then I need y squared, but remembering that y is equal to this and needing everything in terms of x's, And I'll have to take that area times the thickness. And then I'm grabbing my calculator. And if you calculate this correctly and press pause and do it, and see if you agree, mine should be 4.189. So that's how we're going to find volume, by slicing the figure into cross sections and adding the volumes of every one of those cross sections together.